Okay, thanks. Okay, so what have we learned so far? Let's do a recap as usual. Kita stop dekat before power. So we stopped here, I think. And we already drew the circuit. Okay. So let's new slide. I'm gonna pick myself. Okay. So I'm over there. Okay, so far we have learned about Ohm's law lah yang paling senang. Ohm's law, which is V equals to IR. V is in voltage, B is in voltage. V is voltage, which is in voltage. I is current, which is in ampere. And we talked about resistors a little bit. And resistors is in ohms, and you've seen this in high school, so it shouldn't be a problem. And then there is a graph. Sekejap, saya tengah gagap lagi ni, I don't know why. So from the Ohm's law we can plot a graph, right? So if you plot I over here and V over here, which means that your equation will be your equation will be I over V, which gives you 1 over R. So your slope is 1 over R, and vice versa. If your V is your y-axis and your I is your x-axis, so this will become V over I, and then you will get R as your slope. So that's pretty easy. And what else did we learn? We learned about resistors. Resistors. Which is a different color. We talked about resistors, whereby resistors, it slows down the movement of current. It slows down. It reduces the rate. Reduces the rate of charge flowing through a conductor. Reduces the rate of charge flowing through conductor, because it is actually macam restraining current, and we know current is Q over T. Okay, so I is the rate of charge flowing through a cross section. Okay, whatever that goes into the cross section, that is Q over T, so that is I. And then we talked about else. What else did we talk about? Sikit je. Betul lah kot sikit je. Okay, and I talked about for a circuit, you need to have slide. So for a circuit to work, you need to have a closed circuit and also a battery. So let's say that we have a bulb over here. So it must be closed and it must have a source, which is your battery. And there is a component that is using up the battery lah. Component that uses up the energy or the electric potential energy or the battery. Okay, so this is the condition for a circuit to work. And then we talked about parallel and in series. And ni kita cakap daripada chapter 17 from last week. So remember parallel, if I have a battery over here and I have a resistor over here and a capacitor over here, the resistor and capacitor is parallel to the battery. How do I know if they are parallel? They are connected by the same dots on both sides. If your battery is connected by the green and by A and B, by another component, let's say a resistor is over here, we cannot say it's in parallel because this resistor, sorry, cannot put it there. Where should I put it? Let's just put it there. So I can say that the resistor is in parallel with the battery, but sorry, this resistor number 1 is parallel to the battery, but the capacitor and this resistor is not, unless I find out, what am I doing? Unless I find out the equivalent impedance, which we have not talked about yet. Impedance, nanti kita akan cakap. Impedance ni macam a general name for resistors and capacitors, and ada lagi satu benda saya tak ingat nama dia. It starts with an L. Ke inductors, tak ingat. Okay, so resistor, we call it resistance, right? Resistance. And then for capacitor, we call it capacitance. But there's another word, it's called inductor, and we call it inductance. So these things is under the same umbrella, and this umbrella is called impedance. This is what I mean by impedance. Okay, so that's for later. So that I think that's it for recap. Okay, so we are continuing with electric power today. So if potential energy between the terminal battery is V, okay, so this is, you have your source, which is your V. Your V gives you the terminal, the potential difference. Your battery gives you the potential difference because battery either positive and negative. So it gives you the potential difference between the battery terminal, and the charge delivered by the battery is Q. The change in potential energy is given by, okay, so this is du, okay, that we are talking about the change in potential energy. We know that potential energy is U. So if I'm talking about change, I have to put in delta, or in the math world, we use D. Selalunya lah pakai D. Okay, so du is equal to V dq because we've seen the equation where U is equal to VQ. Was it VQ or delta VQ? Delta VQ. Oh yes, it was delta VQ. So if it's delta U, then it's delta VQ. By here, we are talking about the change in your charge. So if I'm talking about delta U, I need to satisfy the delta on the other side as well. But my V does not change because my battery does not change, right? My battery is just a constant value. So the delta goes to the Q. Okay, so this is how they construct this equation. So from this, du equals to v dq. They differentiate this equation, du dt, with respect to time. So dq with respect to time times v. So we know that q is equal to it from this equation. I equals to q over t. So they just like flip this equation to become q equals to it. They just substitute it inside here. It becomes dit over dt times v. So dt over dt cancels out. You get your iv over here. Do you have to know how to derive it? No, not really. I'm just like telling you how you get the equation. You just need to know that P is equal to IV. Okay. Maybe you need to know this one as well. This one. Okay. Oh, yang ni kita dah belajar chapter 17. So yes, you need to know that equation. Chapter 17, right? If you guys still remember. Okay, so P equals to IV, and if using Ohm's law, which is V equals to IR, I can substitute this dude over here, which gives me, so P equals to IV, so I times IR gives you I squared R if you want to eliminate the V. If you want to eliminate the I, you know what to do, it becomes V over R. So you substitute, sorry, I equals to V over R. So you substitute this for I, so this becomes P equals to IV. So I is V over R times V. You get V squared over R. So I know you've seen this, but it's okay. I'm just going to repeat myself. No, not myself. I'm going just to repeat this content because some of you have forgotten. So that is that. So power is in watt. Okay. This is like common knowledge at this point because energy is in joules, right? Energy is in joules, and energy over time, it gives you joules over time, which is simply watt. Okay. Let's do this question. Ada solution dah. Okay. So a small bulb draws a current. So I is equal to 0.2 ampere. When a potential difference across it is 2.5. So it's saying potential difference across it. What does it mean when you say potential difference across it? So you have a bulb. Let's say your bulb is here. I don't know how to draw a bulb. Oopsie. Yeah, I have to take this call. Lemak. Lemak dah hilang. Oh no. Tak lah. Okay, so I have a bulb and the potential difference across it is, oh, okay, kejap. This is important. Okay, sorry guys. I had to take that call. It was about my son's hospital appointment, so it's important. Okay, so I is 0.2 ampere, right? When a potential difference across it is 2.5. Okay, so 2.5 volt. Find the resistance of the bulb. So I don't know if I've told you. I think I have not. All components have some sort of a resistance to them. I told you that the bulb, it allows current to flow through, right? However, for current to flow through, it needs to have some sort of, bukan some sort, a small internal resistance. Small internal resistance. Okay, semua komponen ada, semua device will have a small internal resistance. But we don't call it resistor. We don't call it as a resistor because the function of a resistor is to solely provide you the resistance of the current. But for a bulb, the function is to give light, right? So we don't say, okay, the bulb is a resistor. No, we don't say the bulb is a resistor, but the bulb is a bulb. But it will have an internal resistance. So if I say a current flowing through here is 0.2 ampere, it means that according to Ohm's law, we will have some resistance lah, right? So according to Ohm's law, we know that it's V equals to IR. Our V is 2.5. Our I is 0.2. And this is the resistance of our bulb. So 2.5 divided by 0.2 is 12.5 ohms. Okay, so this is your a bulb. When you read the spec sheet, okay, tahu kan spec sheet tu apa kan? When you buy something, you get the specification sheet. And it tells you, okay, so the I is what, the voltage is what. Sometimes they give you the resistance of the component as well. Okay, so it's just the characteristic of the component. Okay, moving on. An electric kettle draws a current of 5.2 amperes when connected to a 240 volt source. What is the resistance of the heating element of the kettle? Okay, so heating element sama juga macam the bulb. The function is to provide heat, right? So the function is not to be a resistor, but it has resistance. So we can calculate that using Ohm's law. So V equals to IR. V is 240. I is 5.2. So we can calculate for the R. So that is just 240 divided by 5.2. Oh, I wish our brain was equipped with a calculator because I just like, it's just a waste of time. Harap in the future boleh. 46.15. Oops. Okay, so what is the power rating of the kettle? So power is P equals to IV, right? Or I squared R, or V squared over R. So IV, we have the I, we have the V. Let's just use that one. 240, 5.2. Okay, so if you've been reading spec sheets, you know what power rating is. It just gives you the watts, right? 240, I think you have because you've been doing the presentation. So 1248 watts. So that is that. How much energy is used in 30 minutes? And P is equal to energy over time. So that is 1248 watt. So how much energy is used in 30 minutes? You substitute time for 30 times 60 seconds. It should be in SI. So this is 30 times 60. Okay, so use your calculator. So you will get 1248 times 30 times 60, 2.25 times 10 to the 6 joules. So here they use the term U. Okay, so that is more accurate because we are talking about electric potential energy. So you can use E, you can use U, but the more accurate term is to use U. As long as you are using the right equation lah. We know that P equals to E over T or U over T. Okay, you will get the same answer. Okay, so that is the end of that subtopic. We are moving on to DC components. This is the next one. So here in this subtopic, we are going to learn the difference between EMF and terminal voltage of a battery, calculate the resistance of a resistor instead of like a bulb or a heating element. Now we are talking about resistors for sure. Explain the temperature variation of resistance and calculate the resistance of a resistor at different temperatures. Okay, so there's another equation coming up. Okay, so what is an EMF source? So ada resistor juga. Okay. So the potential difference between the ends of a conductor is provided by the EMF source. We know this already. When we have a battery, we are giving the circuit potential difference. When we have potential difference, we can let charge flow through. without the potential difference, there is no way that they want to move on their own. So we have to provide this. The rate at which the charge moves is dependent on the resistance, right? Because I is equal to Q over T and V equals to IR. So when you have a high R, assuming that your V doesn't change because you are using a constant battery, your I should be decreased. So the rate at which the charge moves is dependent on the resistance. So a high R gives you a smaller rate of charge moving. Yes. So a low R gives you a faster rate of charge moving, right? So this is imposed by the resistor. Okay, so that was an introduction. So electromotive force is the electrical energy per unit charge. So E over Q, electrical energy per unit charge. The symbol for electromotive force, or EMF, we call this EMF, or here, electromotive force or EMF is given by this symbol. I don't know what it's called. What is the Greek Latin name for this? But this is how you draw it. It is energy over unit charge. So it is the energy that is required to flow, to force the charge to flow, lah, right? Because that is what the battery does. It gives the force necessary to move the charge. So an EMF is defined as the ratio of electrical power which it generated to the current I flowing through it. What? So basically it's saying that we know that this equation, we have the power equals to IV, right? But this is voltage of a battery. For EMF, you just substitute I, fancy E. So EMF is P over I, okay? And we know that P is equal to energy over time, so E over IT, okay? So these are the equations. This is the equation that you need to remember, because the rest you can just substitute, assuming that you remember P equals to IV and this guy over here, and E over T is equal to P. So these are the variations of EMF punya equation, okay, through substitution. Okay, so internal resistance. We talked about internal resistance for components just now, which is the heating element, the bulb. Even though they provided the function of lighting up the room, heating element gives you heat, but it also has internal resistance. So a battery also has this, because a battery is also a component, right? So this is like a little bit weird concept to grasp, because kita selalu assume battery is just like a source. Like, how can it have internal resistance? But actually it has internal resistance. So a real battery has some internal resistance. Therefore, in a complete circuit, the terminal voltage, the voltage of the battery, the voltage of the battery, terminal voltage is battery, is battery, is less than the EMF, which means that the EMF is the, like the, how do you say this, total lah, like the, I don't know, it's the EMF. Okay, so V is going to be less than EMF. So V, because a battery has internal resistance, the voltage is smaller than the EMF. So there is a way to measure the voltage of a battery versus the voltage of an EMF. So this is how we do it. So for in a closed circuit, which means that there is no open switch, everything is closed, the voltmeter measures the terminal voltage, or it measures the battery. Okay, so the voltmeter is in parallel with this dude over here. This is our battery. However, when we have an open circuit, the switch is open. Okay, so which means that there is no current flowing through. When there is no current flowing through, the internal resistance does not work because there's no current flowing through. So what we are measuring is actually we are measuring the EMF, or like the, I don't know, we are measuring the EMF. Okay, I'm going to repeat myself here. So when we connect a battery to a closed circuit, our current flows through. When our current flows through, it flows through the internal resistance of the battery. Okay, so which means that the battery will lose some power to the resistor, which makes the voltage smaller. Okay, so they lose energy dekat resistor, right? Because the resistor uses up the electric potential energy. So the ones left is the battery. Now, when we put in our a battery in an open circuit where the switch is open, there is no current flowing through. When there is no current flowing through, we are not losing energy to the internal resistance because no current is flowing through, which means that we are just measuring the EMF. Okay, EMF. Okay. Okay, so the terminal voltage is given by V battery. Terminal voltage means battery equals to EMF minus internal resistance times current. So small r is called internal resistance, whereas capital R is the resistance of a resistor. So R is not equal to R, okay? Capital R is resistance of regular resistors. Small r is the internal resistance of your battery, okay? So this is the equation. So V is always less than EMF. V is always less than EMF. So to get this equation, basically V needs to be less than EMF, right? So at EMF minus internal resistance times current. Sorry, current times internal resistance. Okay. An AA 1.5 volt torchlight. What does AA mean? A 1.5 volt torchlight battery. Oh, it's a battery. Sorry. So this is your battery, AA, has an internal resistance of 0.4 ohms. So this is your internal resistance, 0.4 ohms. And your V is 1.5 volt. What is its terminal potential difference? Oh, so if it's asking terminal potential difference, it's asking what is V, which means that this is EMF. Supposedly, I hope I'm right. Okay, so it's asking what is its terminal potential difference. So it's asking for V when it supplies 50 milliampere current to the load. So I is 50 milliampere or 50 times 10 to the minus 3 ampere. So we have our equation V equals to EMF minus current times internal resistance. EMF is 1.5 minus 50 times 10 to the minus 3 times our internal resistance, which is 0.4. Okay, so that is how you do it, I think. Yes, so we are correct. So the answer is 1.48 volt. Okay, next one. A dry cell delivering 1.5A. So I is 1.5A has a terminal potential difference of, so this is the word, terminal potential difference, which means this is your battery, V. V is equal to 1.25 volt. It's asking what is its internal resistance, R. If its open circuit potential difference is 1.5. Remember, open circuit means the current is not flowing through, so it is measuring EMF. So the EMF is 1.5 volt. Okay, open circuit. So this is open circuit voltage. This is closed circuit voltage. Because closed circuit, dia ada internal resistance times current. Okay, so our equation is V equals to, oops, V equals to EMF minus IR. EMF is 1.5 times 1.5 R. R is what we are trying to find, silap tulis 1.5 A, 1.5, 1.25. Okay, 1.25. Okay, so R is, use your calculator. Okay, so V equals to EMF minus IR. Basically just plug in the values. Pretty easy, I think. So far, all the equations are easy. Okay, so now we are going into resistors. Yang ni slightly harder sikit je. So resistors, we know what resistors do. They provide obstacles to the current. Bukanlah provide, dia bagi susah lah current tu nak lalu, because it actually impedes the flow of current or impedes the movement of charges through the wire. So it it has obstacles lah inside. That is like visual aid je tau. Sebenarnya tak ada pun benda-benda yang bulat-bulat ni. Okay, this is just visual aid to make your understanding easier. Okay, so the resistance of a conductor is proportional to its length, which means that the longer your length is, the more obstacles that the charge has to pass through, right? So it makes your resistance increase when your length increases sebab obstacle length lagi panjang. And inversely proportional to its cross-sectional area. So remember, we are moving charges into a cross-section. So the bigger your cross-section, the easier it is to flow. When your cross-section is smaller, the harder it is to flow. So this makes the resistance inversely proportional to the area or the cross-sectional area. So a cross-sectional area that is greater will make the resistance go down. Okay, so this is like common sense. So this gives us an equation where R is equal to rho times L over A. What is rho? Rho is called the constant, it's called the resistivity. But it is constant depending on the material. So let's say, oh, we have a table. Let's see. Okay, yeah. So this is the equation. R is proportional to length. The longer it is, the more obstacles the current has to flow through, the charge has to flow through. The greater the cross-sectional area, the easier it is, right? So R is proportional to length, is inversely proportional to area. And then, of course, we need to have a constant at the front of something that is proportional or inversely proportional. And that constant is called resistivity. And the symbol is rho. Okay, so here we have the resistivity constants for the material, for different materials. For example, by common sense, we know that the resistivity for a conductor will be small, and for an insulator, the resistivity will be super high, right? Because insulator tak kasih charges lalu, right? They just don't like charges to flow. So your resistivity for an insulator should be high. Resistivity for conductor should be like super low, whereas semiconductor should be like mid-range. Okay, so let's see, zinc, tungsten, nickel, copper, constantan, I don't know what this is. So the resistivity is 5. This is in the order of times 10 to the minus 8. Whereas for an insulator, the resistivity is times 10 to the 14. Times 10 to the 14, yeah, to the power of 14. So like this is like super huge gap here. So you can imagine how hard it is for a charge to flow through an insulator. Okay, so typically we just say the charge doesn't flow through because it is super hard. So conductors have this magnitude for resistivity, and semiconductors should be in the mid-range. Why is it erasing? Oh man, what happened? I can't use it. Okay, so this is, kenapa jadi eraser? Why you do this to me? Okay, never mind. Let's see if it works on the next slide. Oh, there's another thing that I needed to tell you. Okay, so we have resistivity, conductivity. So resistivity is rho. You can't write. Boleh pula. Okay, so resistivity is rho. So resistivity is rho. So conductivity is actually 1 over rho. 1 over rho, I think. And then it's inverse lah. Sebab dia opposite conductivity and dia conduct. So resistivity impedes. And then we have a temperature coefficient. We've seen this in chapter 14. It's called alpha. Gendutnya benda ni. Tengok tu. It's called alpha. Boleh pun. Okay, so alpha ni kita dah tengok, and we are going to see it again today. So resistivity is rho, conductivity is, we have this symbol. I think it's called sigma. Wait, apa? Next slide. Okay, is this called sigma? I don't know. So this is the symbol for conductivity, 1 over rho. Rho is 1 over conductivity, dia terbalik. Okay. So those materials with high conductivity are called conductors. Those materials with low resistivity are called conductors, yes. Those with low conductivity are called insulators, and insulators have high resistivity. Okay, so basically 1 over rho is conductivity, and 1 over conductivity is resistivity or rho. Okay, so this is where we see our temperature coefficient again. Previously, we talked about temperature coefficient in equation delta L over L naught equals to alpha delta T, right? In chapter 14. Let's hope my pen works now. Hello, no, it's not working. Okay, let me see first. Okay, tutup jap. Save. Sekejap korang. What time is it? Oh, it's 11:11. Any questions so far? Everyone's okay, still alive after 3 classes back to back. Apa ni? Okay, boleh dah. Let's hope that it stays with us, this pen. It needs to be classmate as well. Okay, so resistivity and temperature. For most metals, resistivity increases with increasing temperature. Oh, before that. It's not working back. Apa saja benda ni? Okay. Maybe I need to calm down. Okay, so previously we talked about chapter 14 about temperature coefficient. This was the equation. Kenapa bila nak cakap pasal L ni tak dapat? Okay, I think we should take a 5-minute break while I fix this. Go get your water, up to food ke whatever lah. Okay, 5 minutes. Sekarang is 11:12. So let's come back at 11:17 while I fix this thing. Pausing share. Pausing.